In this video, we introduce the Theorem of Pythagoras, possibly familiar to many of you from school. We'll look at it in the context of an interesting historical perspective relating to Babylonian mathematics. An application of this theorem is a geometric interpretation of the square root of 2, a very important real number in the history of mathematics. We prove that the square root of 2 is irrational, that is, cannot be expressed as a fraction, a result that was known to the ancient Greeks. We begin the story by considering a unit square with side lengths 1 unit. I'll reproduce the unit square. If you start off at, say, one corner and travel to the opposite corner, you could, for example, move along the sides of the square. But that's not the most direct path. The most direct path from one point to another is a straight line. If we go along the diagonal of the square, that's the shortest path, and it has a certain length. We'll call it x. So what I'm going to do is play around with this square. This is a trick that goes back to Babylonian times. So here we have a unit square, and I've just taken a copy of it, and I've formed a stack with 2 squares. I will just put another stack of 2 squares next to the original 2 squares to create a 2 by 2 square. So I've got 4 unit squares making a larger square with side lengths 2 units. Now I'm going to focus on the midpoints of the sides of this square, and then join up these midpoints by forming diagonals in this way. Okay, now notice something. In the middle of this 2 by 2 square is another square whose side length is x, the length of the diagonal of the unit square. And that inner square has an area which is x squared. Okay, now I can count the area by adding up the areas of certain triangles in this diagram. If I shade that triangle, then that has area which is a half of a unit square. Then I add the area of this triangle, another half, the area of this triangle, and the area of this triangle. So I'm adding a half 4 times, which gives you 2. So the area of the inner square, it's all shaded now in green, is 2 units. So x is a number whose square is 2, so x is the square root of 2. Okay. Now I'm going to do something. I'm going to copy this figure, and I'm just going to rub out everything outside that green inner square. And then I'm going to get some clay. So I've got some soft clay, and I've imprinted on that clay an image of that inner square that we've been discussing. I put it in the oven and bake it, and then a few thousand years later, this is what we get. Okay? This is called the Yale tablet, and it's the oldest recorded proof of the Theorem of Pythagoras, and in fact predates Pythagoras by about 1,000 years. Now what's this got to do with the Theorem of Pythagoras? Well, let's go back to the unit square and its diagonal, which is the square root of 2, which we've demonstrated by that method. This is what's called an isosceles triangle, where the shorter side lengths are equal, in this case to 1. I can draw another isosceles triangle, which could be much bigger or much smaller, with common side length a. We scale up the lengths of the smaller triangle, so the hypotenuse of this new isosceles triangle is root 2 times a. Okay, and if we call that c, then c squared is root 2a all squared, which is 2a squared, which is a squared plus a squared. Right. Now perhaps you can see that this starts to resemble a familiar result. The square of the hypotenuse is the sum of the squares of the other 2 sides. This is a special case of a general theorem, the Theorem of Pythagoras, which says if you take any right-angled triangle with side lengths a, b, and hypotenuse c, and a and b can be different now, if you form squares on each side of the triangle, then the square of the hypotenuse is the sum of the squares of the other two sides. So we get this famous equation, c squared equals a squared plus b squared. And this is the Theorem of Pythagoras. And what we discussed earlier was, in fact, a proof of this theorem in the special case where a and b are equal to 1, which clearly scales up to a and b being equal. Now you can modify that proof very easily to get a general proof, and that modification appears in the notes that accompany this video. Now if we have a look, c squared equals a squared plus b squared implies that c is the square root of a squared plus b squared. Now when you have an expression involving a square root sign, it's called a surd expression. Okay, and you don't expect it to simplify. Occasionally it will. For example, if I take a right-angled triangle where the shortest side is 3 units long, the other short side is 4 units long, then the hypotenuse turns out to be 5 units long. Okay, so you have what's called a 3, 4, 5 triangle. The 5 is predicted by this theorem because 3 squared plus 4 squared, which is 9 plus 16, is equal to 25, which is indeed 5 squared. Okay. Now that's very rare that the hypotenuse simplifies so simply. Typically, the surd expression doesn't simplify, and if we go back to the unit square, triangle associated with the unit square, the hypotenuse has length root 2, and it turns out that root 2 cannot be expressed as a fraction. Okay. Now, of course, the distance between 2 points is very important, and ancient mathematicians wanted the mathematics to be sufficiently powerful to model distances between points. Okay. So studying the square root of 2, the diagonal of the unit square, was a very important kind of mathematical entity. And now, when you develop mathematics, you start off, for example, with counting numbers, and then you form fractions of counting numbers. They're called rational numbers. And it was an important question whether the mathematics of fractions was sufficiently powerful to model distances like the square root of 2. And it turned out the answer is no. There is no fraction which can be used to express the square root of 2 exactly. The square root of 2 is not a fraction. Okay, now I'm going to try and explain why this is the case. Now in mathematics, proofs or demonstrations are a little bit like criminal investigations. It's typical to make some kind of supposition and see if it leads to nonsense or a contradiction. Right? If you're investigating a crime and you want to know who was the murderer or who was the thief, if a suspect can produce an alibi that contradicts the possibility of them committing the crime, then you know that they're innocent. And we're going to use that technique in this proof. We're going to suppose, to the contrary, that root 2 is a fraction and see if it produces nonsense. Okay, so I'm going to suppose root 2 is a divided by b, where a and b are counting numbers or integers, and I can assume that we've cancelled off any common divisors in the numerator and the denominator, so that this is in reduced form, and that will turn out to be important. We will square both sides of this equation. On the left-hand side we get 2, on the right-hand side we get a squared divided by b squared. Okay, so if we multiply both sides by b squared, we get 2b squared is equal to a squared. Okay, so a squared is 2 times a counting number, 2b squared, so it's even. Okay, and it follows, you can think about why this is the case, that a itself must be an even counting number. So if it's even, it means it's 2 times something. Say a is equal to 2 times c for some counting number c. So if we go back to the previous line, we've got 2b squared is equal to a squared, But a is 2c, so that's 2c all squared, which is 4c squared. Okay, so now we divide both sides by 2, and we conclude that b squared is 2c squared. So b squared is 2 times something, which is even. And as before, if the square of a number, counting number, is even, the number must be even, so therefore b is even. Okay, now have a look. b is even, and a is even, so they're both divisible by 2. They've both got a common divisor of 2. And that contradicts the assumption that a over b is expressed in reduced form. So this is actually nonsense, can't be true, so therefore root 2 is not a fraction. Again, we've covered a lot of ground in just a few minutes. Much more detail is provided in the accompanying written notes. Please take some time to read and digest them carefully, and then try the exercises that follow. Thank you for watching, and I look forward to seeing you next time.